Good morning. I'm Alex Jehle, a PhD student in the Colorado School of Mines Space Resources program. The co-authors of this work are Liz Scott, a fellow PhD student, and Ross Centers, a master's student. Today I want to convince you that we can use space resources to establish a new economy in space while contributing to solving global warming by building a planetary sunshade, a thin-film megastructure in space that will block a small portion of sunlight from reaching Earth, and we can do it all in my lifetime. Now let's just start by agreeing that global warming is a contentious issue. It's a non-starter for some. Even more taboo is the idea that we need to reverse the anthropogenic, yes, we caused it, reverse the anthropogenic climate change through geoengineering. To someone with an engineering background, global warming boils down to thermal equilibrium problems. The total heat in a system is the sum of heat in plus heat retained less heat out. In our case, the system is the Earth including all of its land masses, its mantle, core, atmosphere, and oceans. The external environment is the sun, which radiates 1361 watts per meter squared at 1 astronomical unit, and space, which acts as a radiative heat sink. These are constants on our geological timescale. What has changed is the carbon dioxide in the atmosphere. It reduces the amount of energy that can be radiated away from the Earth's mass. To prevent the Earth from heating up further, we need to remove the excess post-industrial carbon dioxide in the atmosphere. So long as the energy imbalance is in place, Earth will heat up. We can't make space colder to enable the Earth to radiate more heat, and society is so far unwilling to consume less carbon-based energy. So we can reduce the amount of incident energy reaching Earth from the sun. Can we do it without further polluting Earth's environment? Yes. And we can do it by kickstarting a new economy in space. The late Dr. Paul Spudis was one of the first to point out the moon is full of resources that we can use to make space exploration possible. He helped discover and popularize the fact that the moon has water, aluminum, silicon, titanium, rare earth elements, oxygen, nearly everything you find on Earth. It's there, and it's at a lower potential energy than those same resources found here on Earth, relative to the Earth-Moon or Sun-Earth Lagrange points. Water is life-sustaining. It is also the SLS's chemical propellant. Water is still the best chemical rocket engine fuel we know of, and it's on our nearest celestial neighbor. We want to use those resources on the moon and on near-Earth asteroids to construct a planetary sunshade at the Sun-Earth Lagrange point 1. It's going to be huge. Maybe you're not interested in climate change. It's a generational thing. A lot of older folks aren't. But you are excited about space resources utilization, and that means you're excited about political support for investment in space. On the left are the results of a poll we took. 1,000 people were asked if they'd rather support a space-based solution to climate change or a city on Mars. The answer was 2-to-1 for a space-based solution to climate change. Fortunately, the goals are complementary, but we think climate change sells better. On the right is a poll from Pew Research Center on Americans' preferred NASA priorities. On top, climate and planetary defense. On the bottom, the moon and Mars. Again, these goals are complementary, but it's clear that people are much more interested in protecting Earth. So even if you're not interested in climate change, if you're interested in large-scale space resource utilization, the planetary sunshade could be a path to your dreams with popular support. And climate change is a generational issue. However much any of us care about climate change, we know that the kids behind us care more. These are some of the more motivated members of the coming generation. They look like they might run for office someday. In 2050, kids like these will dominate the electorate. So say you're interested in large-scale space resource development mid-century. What would you like to bring to the table when negotiating for combustion permits with them? A plan to stop or reverse the effects of global warming might help with that. Seem far-fetched? In 15 years, California will ban the sale of internal combustion automobiles. Progress in space is built on dreams. SpaceX's dream of a city on Mars has brought a lot of energy into the broader space community. It's a major driver for interest in space resources today. We're trying to expand on that dream with a green, Earth-sustaining cislunar complement. If we're successful, we can bring more people into space resources community and resolve some tension between spaceflight and environmentalism. There are other benefits to the planetary sunshade than just temporarily reducing the sunlight reaching Earth. It would be a shame to block all that sunlight without capturing the energy and putting it to good use. So we'll make the sunshade from thin-film photovoltaics. Sunlight is not the only space resource we will harness. On the other side of the solar panel is the darkness of space, a natural and extremely cold radiative heat sink. We have everything we need in space to turn the sunshade into a data storage or supercomputing center, as silicon is the 10th most abundant element in the solar system. And if you can imagine other uses for a lot of energy with relatively cheap access to a lot of mass, the space resource industry is interested in your project too. Our proposed design consists of modular structures. On the left is an island in the Sunshade Archipelago. It's made of 169 smaller hexagons, each 20 kilometers on a side. Each hex generates 200 gigawatts. The island generates 35 terawatts, twice today's global energy supply. The first hexes could be made in GEO, alongside space solar power stations. They could be attached to factory ships and flown to L1, and used to process raw material launched from the moon. Or they could be used to capture sunward asteroids, redirecting them to L1 for processing. Either way, to get this thing built, you need to use the first building blocks to make more, harnessing exponential growth. In doing all this, you also build a civilization-altering industrial capacity out at the edge of Earth's gravity well. It would put us on the Kardashev scale. Because the architecture has to build itself, it's also a factory. The fringe benefit to saving our climate is that you get to build a space megastructure that makes space megastructures. If we can build this, human expansion throughout the solar system becomes easy. This is a worthy vision, and every step towards its construction builds the space resources economy. We determined that we need between 5 and 22 of these based on the Intergovernmental Panel on Climate Change's range of forecasts. Last year, the IPCC published an emissions gap report detailing how much carbon dioxide emissions we need to cut to only inflict a range of 1.5 to 2 degrees Celsius increase in average global temperatures over the next 100 years. Here, the y-axis depicts annual gigatons of CO2 emissions. The x-axis is time. In order to only see a 2 degrees Celsius warming, the Earth must reduce emissions by 10% in the next 5 years, and by 60% in 30 years. To see only a 1.5 degree increase in global average temperatures, we need to reduce our global emissions by half in 10 years, and by 90% in 30. I hope we can do it. Even with 1.5 degrees, we are going to see mass extinctions, increased wildfires, beyond what the West Coast is already seeing, rising sea levels. The problems go on. If you want to study the problem more, the IPCC report has been broken down nicely by Alan Buis of NASA. A degree of concern, why global temperatures matter. Clearly, reducing emissions is only part of the solution. Zero emissions will still result in global warming without removing CO2 from the atmosphere. The outlook is grim. We have missed the emissions gap set by the Paris Accords too. So let's reframe the problem. The representative concentration pathways charted here predict the temperature increase over the next 300 years based on the energy imbalance in watts per meter squared. The RCPs are numbered based on their corresponding watt per meter squared daily average imbalance in energy, how much energy is retained by Earth in excess of pre-industrial pollution levels. Here, RCP 2.6 is shown resulting in maintaining a 1 degree increase in temperatures by 2100. RCP 8.5 would result in a 3 to 5 degree increase in temperatures by 2100. Critically, this gives us a target of reducing the incoming sunlight by between 1.9 and 8.5 watts per meter squared. Now let's do some math. Insolation at 1 AU is 1,361 watts per meter squared. Averaged across the surface of the Earth's sphere, 4 times its cross-sectional area, is 340 watts per meter squared. This includes both the daytime and nighttime sides. This needs to be reduced by between 1.9 to 8.5 watts per meter squared. That's a 0.56 to 2.5% reduction in incident sunlight. We need to create a partial eclipse of the sun worldwide by between roughly 0.5% to 2.5%. Let's think about solar eclipses and then consider lunar eclipses and what we are trying to accomplish with the planetary sunshade. A total eclipse occurs when the observer is in the occulting object's umbra. That is, the observer cannot see any of the sun's otherwise observable surface. The moon appears bigger than the sun. A partial eclipse happens when the observer is in the penumbral shadow. The occulting body, typically the moon, is offset from being centered on the sun. Finally, an annular eclipse, an eclipse that only partially obscures the sun, but where the entire moon appears to be surrounded by the sun, occurs when the moon appears smaller than the sun. We want to create an artificial annular eclipse that only eclipses 0.5% to 2.5% of the sun's surface. Let's start by conceptualizing a total eclipse of the Earth again to determine what 100% of the incident sunlight actually is. Here's the sun and the Earth. We trace the extent of sunlight reaching the outer edges of Earth's atmosphere and trace them until they intersect behind the Earth. We call this point P. Incidentally, it happens to be the furthest point of Earth's umbra, where Earth's shadow transitions between the umbral and antumbral point. It also allows us to define a conic cross-section around the Sun-Earth-Lagrange 1 point that would represent a 100% blockage of sunlight. As viewed from point P, the Earth completely, if just barely, eclipses the Sun and the cross-sectional area here. Using some spherical geometry, we can calculate the distance to point P and then calculate the representative area that would completely eclipse the Sun across all of Earth's surface and atmosphere. The area is no surprise. It's about half a steradian. We get a similar result for the angular area of the Sun as viewed from Earth. When solving for the area needed for 0.56% of that half a steradian at SEL, we find that it is 857,000 square kilometers. For RCP 8.5, we need roughly 4 times that amount, 3.8 million square kilometers. This sounds like a lot. It is, but are we really going to block out the Sun? No. The transition of Venus blocked 0.1% of insolation, or 1.4 watts per meter squared. How many of you noticed it take place? 6 islands depicted here in a Lissajous orbit around SEL1, as viewed from Earth, would slightly exceed the RCP 1.9 incident sunlight reduction needed to maintain current temperatures. Up to 22 would be needed for the RCP 8.5 scenario. You would need eclipse glasses or specialized camera filters to see or image them. Best yet, when you no longer need them, as we reduce the total greenhouse gases from the atmosphere, we can easily remove the sunshades individually and incrementally from SEL1. From there, they can continue to serve their additional secondary purposes. Our solution, a planetary sunshade at SEL1, aligns and builds upon previous work by McInnes, Angel, and Sanchez. We wanted to consider what other design space is possible. These went from entertaining, during our brainstorming session, to outlandish, but only one merited serious consideration, a ring sunshade in Earth orbit. There is limited prior research into ring sunshades. Mautner looked into a Leo ring and clearly identified that there would be significant orbital mechanics issues with it that have only partially been addressed with later research into solar sailing, forced motion orbital mechanics. A modular fragmented system may be needed rather than a monolithic structure. To compare concepts, we needed a set of considerations. We settled on mass, delta V, environmental impacts, and localized impacts. That is, whether the ring was close enough to the Earth to cause localized total eclipses or significant partial eclipses. We considered a set of design constraints. First, it would still be a thin film megastructure, so no, it wouldn't result in a halo world. Second, it would be inclined to the ecliptic at 23.5 degrees. Third, to provide consistent shading to meet the IPCC goals, the area would need to be calculated, as seen from Earth's umbra-penumbra point, point P again. Here we approximated the distance as the sum of the radius of the sunshade and the distance from Earth to point P. Only a small section of the halo would effectively cast a shadow at any one time. Because of orbital mechanics, the sunshade would still be orbiting Earth, hence we would need the full ring to provide continuous coverage. So we calculated the total required cross-sectional area that casts a shadow and deduced the height of the ring times the sun's angular diameter, and extended it about the circumference of its orbit. We considered several altitudes, from low Leo, from 500 kilometers in altitude, to Geo, 36,000 kilometers, and to 8 times the height of Geo. Beyond that, at 9 times the height of Geo, an orbit would no longer be stable as it would enter the moon's Hill sphere. Here are the results of the total surface area of a ring sunshade are plotted on the y-axis against the altitude on the x-axis. For reference, the moon is 380,000 kilometers away. The ring sunshade only compares positively to the sunshade at SEL1 in area in the Leo orbital regime. Its surface area is represented by the 2 horizontal lines for comparison, but that is the only positive comparison. The unintended consequences are much greater. At Leo, the possibility of out-of-control Kessler syndrome should be brought up, arguably all the way up to Geo. We should seriously consider this a problem. Micrometeorite impacts, space debris impacts, or even sabotage could set off the Kessler syndrome. At LEO, the advantages of space resources are also diminished, making Earth launch equally or even more economical. The delta V to safely bring all of that mass, asteroids, lunar material, up to 10,000 megatons of mass, is significant. It should also set off alarm bells for its potential to cause a self-imposed asteroid extinction event. This brings us to another thing we have to take seriously. We believe that Starship will meet its design goals. Timeline? Maybe not. But performance? Yes. We'll have prospecting rovers on the moon before Starship gets there, but at a certain point, SpaceX is going to start landing 100-ton payloads. We should be ready for that, ready to utilize the capacity. SpaceX is building the Starfleet for a city on Mars, but what are they going to do with it between Mars launch windows? This is a logistical resource that could build a railroad to the moon. Scaling comes from improvement, and improvement from iteration. We see a world in which you can just fly something to space and try it, or bring your engineering team to the moon and work the problem on site. Humans and robots working together, with fabrication, repair facilities, and other centralized infrastructure, will make the lunar poles a fast technology and resource development site. The moon becomes a factory, a mine, and a gas station. Everything we need to build a sunshade is on the moon, and we can get it to L1 for 2.8 kilometers per second. Progress in space has been slow. With a railroad to the moon, that would change. Since Starship will be so revolutionary, it is fair to wonder whether we can just build the sunshade on Earth and launch it to SEL-1. After all, establishing an entire cislunar economy is going to be complicated and expensive. As amazing as Starship is, the answer to that is no. A sunshade made out of ultra-lightweight, thin-film material weighs approximately 20 million tons. Assuming that Starship achieves its design goals, launching 20 million tons would require 200,000 launches at a cost of $40 billion in launch costs alone. And this is only going to get the sunshade components to LEO. Additional propulsion would be necessary to get them to SEL-1. If launching the sunshade completely monopolized the capacity of the entire Starship fleet, it would take over 66 years to launch the mass needed. Fortunately, all the materials needed to build the sunshade exist in cislunar space. Starship and other reusable heavy launch vehicles will be instrumental in helping us unlock these resources. As we learned in our Space Resources Fundamentals class at the Colorado School of Mines, there are 3 elements to a space resource utilization plan: an economically extractable resource, technologies to extract, process, and deliver the resource, and customers willing to pay for it. The resources of cislunar space are vast and varied. Some resources are even present in the void of space. These include solar energy to power machines, hard vacuum, microgravity, and thermal gradients to aid in new forms of manufacturing, and even orbital locations such as LEO and Lagrange points, which are optimal for different applications. There are 2 places in cislunar space to extract physical resources: the moon and near-Earth objects, mostly asteroids. The moon will likely be the first source of space resources, since it is the most studied location. The moon is rich in silicates and metal oxides, which can be used to make glass, silica, titanium, aluminum, iron, and oxygen. Creep soil can provide rare earth elements for use in electronics. The lunar poles also contain a high concentration of water, which can be electrolyzed into hydrogen and oxygen to make propellant for a cislunar logistics network. The resources from NEOs are more varied than those of the moon, although they are not as well understood due to relatively limited prospecting to date. Hydrated minerals, hydrocarbons, and organic compounds, silicates, and metals including rare earth and platinum group metals can all be found in large quantities in asteroids throughout cislunar space. These resources are often available for a lower delta V than those on the lunar surface. Asteroids can also be redirected to SEL-1, where they can be safely processed into materials for the sunshade directly at the point of final construction. NEOs will be a viable source of resources in the later stages of sunshade construction, and once they are fully utilized, will eliminate the need for resources other than humans to be launched from Earth. A project on the scale of the Planetary Sunshade represents an all-of-the-above use case for cislunar resources, and so technologies all through the value chain must be developed to extract, process, transport, manufacture, and assemble them. Fortunately, active research and development is occurring in each of these categories. This work is ongoing in academia, at private companies large and small, and within civil space agencies such as NASA and the ESA. None of the technologies shown in this slide are science fiction. They all represent existing tech demonstrations or designs, or in the case of the international efforts to assemble the ISS, established technology. Technology demonstrations will evolve into small prototypes and eventually operational production. Advances in the heavy launch industry will enable rapid, relatively inexpensive design iteration, which will allow progress at an exponential rate as each success builds upon the last. As these and similar technologies mature, they will increase in capability until they can produce structures on the scale of the planetary sunshade. At that point, we'll have a fully functional cislunar economy capable of building anything we can dream of. The most important part of a space resources utilization plan is the customer. This has unfortunately been the stumbling block for space resources, with a few notable exceptions, such as NASA and the United Launch Alliance. No customer has stepped forward to offer to buy space resources at a price that justifies the huge investment required to find and produce resources from space. Space resources has been, thus far, a solution in need of a problem to solve. Climate change, represented by this image of North America in a world without ice, is clearly a problem in need of a viable solution. We have thus far been unwilling to even slow our carbon emissions, much less start the arduous process of removing carbon from the atmosphere. Other forms of solar radiation management come with unfortunate side effects, such as increased pollution to our atmosphere or oceans, and the effects of climate change are already here and getting worse. Increases in wildfires, heat waves and hurricanes, climate-driven wars, and forced migrations, the emergence of global pandemics. The planetary sunshade marries the problem of climate change to the solution of space resource utilization in a way that maximally benefits Earth and its inhabitants, while providing a customer for the establishment of a cislunar economy. The ultimate customer for the planetary sunshade is everyone who will eventually be impacted by climate change. In other words, everyone on Earth. As the effects of climate change continue to escalate, concerned citizens will force their governments around the world to take action and develop solutions. Right now, we are conditioned to believe that government action on climate change is impossible, especially action as audacious as the sunshade. However, today's inaction only escalates the climate crisis and hastens our thermodynamic inevitability. At some point, the impossible will become inevitable. What happened to the O'Neillian dream of millions of people living and working in space? Some are working on it, slowly, ferociously, but the planetary sunshade could be a credible technological and economic driver, marshaling civilizational resources towards that goal. Because space resource utilization requires not just resources and technology, but a customer. The resources to build a planetary sunshade are abundant on the moon and on near-Earth asteroids. The space resource community is developing the foundational technologies. The limit to the scope of our vision is really the customer, and there is no bigger problem than climate change, which affects all of humanity. There is no good terrestrial solution, short of slowly removing all that carbon out of the atmosphere and putting it back in the ground. From a marketing perspective, the planetary sunshade is the biggest possible product that space resources could offer. Nothing else could deliver as much value to Earth. Unlocking the value seems hard right now, but we have learned to live in a world where governments do not act on climate. The future will not look like the past.